أعزائي الطلبة، راح أبدأ وياكم اليوم ب review of the synchronous machines، وإذا يسمح لنا الوقت نقدر نحل لكم بعض الأسئلة. إذا ما في وقت نعمل لكم فيديو ثاني لل examples و problems. مثل ما تعرف إنه synchronous machines تختلف عن الأنواع الأخرى من الماشينز، يعني induction motor، DC machines أو transformers، كلها عندها سبلاي واحد. السynchronous machines لها AC supply للستيتر و DC supply إلى الروتر. الروتر DC supply الفيلد كارنت IF يولد الفلكس، الفلكس يقطع ملفات الارمتشر ويولد generated EMF في حالة الجنريتر، وباك EMF أو induced EMF في حالة الموتر. synchronous machines من التسمية مالتها rotates at constant speed اللي هي NS synchronous speed تساوي 120 F على P، وإذا NS ثابتة معناها الفريكونسي راح يكون ثابت يساوي NS times P على 120. مثل ما تعرف من معادلات الترانسفورمر والاندكشن موتور، ال EMF اللي نسميها excitation voltage هي EF تساوي 4.445 FN kW. kW هو الوايندينج فاكتور، N number of turns per phase، F frequency، phi F is the flux. The flux is produced by the field current IF, and we can write EF is proportional to NS times phi F, and for constant speed or constant frequency, a given frequency, then EF is proportional to IF. The equivalent circuit for the motor or generator is, as you can see, consists of EF, the induced or generated EMF. XS is called the synchronous reactance. RA is the resistance per phase of the stator winding, where VT is the terminal voltage. Now, this circuit, if the current is coming out of the circuit, then it's working as a generator. This will be the source EF, and VT here will be the sink. If the machine is working as a motor, then the current IA is going into the machine, and this VT will be the source and EF will be the sink. Now, XS is equal to XAR plus XAL. XAR is called reactance of armature reaction, or you could call it magnetizing reactance, and XAL is the leakage reactance of the per phase of the stator winding. This is similar to the leakage reactance X1 in the induction motor or X1 in the transformer. We also have ZS, which is called the synchronous impedance, which is equal to RA plus JXS. Now, if we come to the values of these parameters, normally for small machines, RA is always less than XS. Now, we talk about orders of magnitudes. XS for small machines is about 10 times RA. For large machines, for example, generators in power stations, or big synchronous motors. You're talking about powers in thousands of megawatts or hundreds of kilowatts for motors. XS could reach almost 100 or 120 times RA. So in most of our calculations, we neglect RA and we assume that ZS equal, the magnitude of ZS equal to XS. This will result in a very, very small error, but it will make life much easier for the calculations. Now, if we come to the phasor diagram, the EMF equation for a generator, EF is equal to voltage drop across the impedance here plus the terminal voltage, VT plus IARA plus JIAXS. EF, if we neglect RA, it becomes VT plus JIAXS. For a motor, it's the opposite. The source is VT, so it's going to be EF equal to VT minus JIAXS. Now, to draw the phasor diagram, let us consider the three cases we have of the stator current. Stator current could be lagging power factor, or stator current IA lagging VT, or it could be a unity power factor, or we have a leading power factor. Let us have a look now at these three cases for generator and for a motor. If we look at the phasor diagram for a generator, if we start with the lagging power factor, forget about the motor now. With a lagging power factor, then VT is always taken as a reference terminal voltage per phase. IA is lagging. Now the excitation voltage EF is equal to VT plus JIAXS. As you know, if you multiply any vector by J, then it will rotate by 90 degrees counterclockwise. So this will be JIAXS, and the resultant is EF1. This angle between EF and VT is very important, and it's called, well, later we'll define it. If we have a unity power factor, IA is in phase with VT, JIAXS will be perpendicular to VT, and this is EF. Again, this is the angle delta. Now, for a leading power factor, we have IA is leading VT, the vector J times IAXS, right? It will be perpendicular to IA3, so this is JIAXS, and this is the EF3, of the excitation voltage 3. These three cases are for the generator. Now, let us have a look at the cases, these three cases for a motor. For a motor, we have EF is equal to VT minus JIAXS. So this is IA lagging, and this will be the vector. The vector IA times J will be in this direction, and minus it will be in the opposite direction, and the angle is delta. If we go to If we go to the second diagram, IA is in phase with VT. Then we draw the phasor diagram, and EF2 is lagging VT. EF1 is lagging VT. And if we come to the third case, we have IA is leading VT, and the phasor diagram will be this way, and again delta is negative, or EF is lagging VT. Delta in all cases is a very important quantity, and delta is called the power angle. Power angle. Delta is always positive for a generator, and delta is always negative for a motor. I'll repeat this again. Delta is always positive for a generator, and delta is always negative for a motor. Actually, this has some physical meaning in the operation of the machine, which is beyond this course. So please, if you calculate something for a generator and you have delta becoming negative, then you cross over your calculation and repeat it again. This is not a mistake. This is catastrophe. The same thing for a motor. Delta must always be negative. Now, if we come to the next topic we have in the synchronous machines, which is power and torque characteristics of the machine. If we consider a generator, this is the equivalent circuit. Now, define these parameters. VT is always a reference, so the angle for VT is 0. EF equal the magnitude of FEF, and the angle delta is because we have a generator, so it's positive. Where ZS equal RA plus JXS, which is equal to the magnitude of ZS and the angle theta S. Theta S is the tan inverse of XS divided by RA. We leave the RA now in the derivation, and then we'll see later what happens when we neglect RA. Now, as you know from circuit 1, the total complex power is S equal 3 VT times IA conjugate of IA. You know the meaning of conjugate. If IA, the angle of IA is, for example, minus 30, then the conjugate will be 30. Now, from this equivalent circuit, EF equal VT plus IA times ZS. These are vectors, i.e. each quantity have a magnitude and an angle. So IA equal EF minus VT divided by ZS. IA conjugate, it will be the conjugate of all this quantity, and it will be EF conjugate divided by ZS conjugate minus VT conjugate divided by ZS conjugate. And if you put the actual parameters, so this will be EF magnitude, and the angle is minus delta because this is the conjugate of EF, and this will be ZS, the angle, minus theta S. Same thing for VT. Eventually, the complex power, total complex power for 3 phases will be S equal S equal 3 VTEFZS angle theta S minus delta, and 3 VT square divided by ZS angle theta S. The real power is P equal S phi times cosine phi, the angle. So the real power will be P equal 3 VTEF Z divided by ZS cosine and 3 VT square ZS cosine theta S. Since we said RA is very small, negligible. If we neglect RA, literally what this means is the ZS magnitude of ZS will have the same magnitude as XS, and theta S will approaches 90 degrees. Now, if we go back to the power equation, real power equation, so cosine 90 minus delta will be sine delta. And cosine 90, as you know, is 0. So the resultant developed power by the machine is P equal 3 VT EF XS divided by XS sine delta. This is a very important equation for the synchronous machines in terms of the power angle delta. We have another, as you know, another equation for the power. Power normally equal 3 VTIA times cosine theta, which is the angle between the current and the voltage. That is the input power. This is the developed power inside the machine, the real power developed inside the machine. Now, if we want to find the torque, the machine is running at synchronous speed, and the torque is power divided by omega, and in this case omega synchronous, and omega synchronous is equal to 2 pi ns synchronous speed divided by 60. So the torque is equal 3 VTEF divided by omega synchronous times XS sine delta. From the power equation and the torque equation, we can deduce that this term 3 VTEF divided by XS for the power is the P max, maximum power. And if we draw the power curve, the power with delta, then we have this curve, a sine function. The same thing, we'll have the same curve, but scaled down by omega synchronous for the torque. Now, there is two examples are given in the book, and my advice is that you should really study these two examples. Example 63 deals with a machine operating as a generator, while example 64 deals with the same machine when it is operated as a synchronous motor. So please read these two examples carefully, and if you have any problem understanding them, send me an email. Next topic, important topic in the synchronous machines, is the power factor control. What is the power factor control? You know that at home you have a bill, فاتورة كهرباء, you pay for the real power you use. in industry, the problem is different. There is two bills, فاتورتين. One bill for the real power, which is kilowatts hour or megawatt hour, and the other one, the other bill you have to pay is kilovolt amp hour or megavolt amp hour. Now, in industry, if you go into any factory, majority of the motors used are induction motors. Induction motors always operate at lagging power factor. What the lagging power factor, what it does, it increases to get the same power, real power, it increases the current flowing into the factory or plant. When you increase the current, you're going to increase the bill. راح تزيد الفاتورة increase the bill by because the current will increase. Normally the voltage is always constant. So if we look at a synchronous motor at constant power, P equal 3 VTIA cosine phi. Hence, Vt is constant. If the power is constant, then Ia cosine phi is constant, which means that if I improve the power factor, I will reduce the current I'm taking from the network, and when I reduce the current, I will reduce the fatura high. This bill, it will be less. Also, the power is equal 3 EF VT EF divided by XS sine delta. Hence, EF sine delta will also be constant. Now, we have three, again, cases to consider this, the stator current. It could either be lagging, unity power factor, or leading power factor. Now, the motor EMF equation is EF equal VT minus JIXS. EF, we called it the excitation voltage. Now, if we draw the phasor diagram for the three cases, three currents, the phasor diagram will look like this. Now, this is the phasor diagram for a synchronous motor running at constant power. This is VT. If we take the first case, IA1, lagging power factor, then we would subtract minus JIA1 XS from it, and we have EF1. If we take the unity power factor, then we have EF2, and leading power factor we have EF3. This line, red line, is called the locus of IA, المحل الهندسي اللي يتحرك عليه التيار. IA يتحرك whatever the value of IA يتحرك على هذا الخط. من أغير الباور فاكتور التيار يتغير. هذا المحل الهندسي ل EF ساين دلتا اللي هي locus of EF. Okay. Now, as you can see here, if we start with EF, lagging power factor, when we increase EF, which means we increase IF, the field current, which controls EF, the power factor becomes unity, and then the power factor becomes leading. So we can improve the power factor of the plant, مصنع, معمل, ورشة. We can improve it by changing the excitation of the synchronous motor The power remains the same, constant, but the power factor will improve. Improving the power factor means that the current will be reduced. Now, this leads us to what is called the V curves of a synchronous motor. The V curves of a synchronous motor. The V curves is the relationship between the current IA, the armature current or stator current, and the field current, which is the DC current IF. This is here the ideal case, ideal machine, i.e. we have no losses at all. And you see at no load, the armature current is zero. There's no. So if we were working at this point of armature current IA, if we increase IF, it will continue IA to decrease until it becomes zero, and then start increasing in a leading, becomes leading. So this from IF2 going right is leading power factor. In this direction is lagging power factor. Now, normally the machines have some losses and they are not ideal at all. So if we take this into account, the curve will be, the V curves will be something like this for the full load, half full load, no load. The reason for this is as you increase IF in this region, then you will go into saturation region and the relationship becomes non-linear. That's the reason. And here we assumed ideal machine and we get the V curve. So here the current will be, even at no load, at unity power factor, the current will be minimum. So if you're working at a point here, let's say, you increase the excitation, IF, you increase IF, you become the current minimum, and then the current minimum at unity power factor, and then start increasing at a leading power factor. When you have a leading power factor in a plant, then you're going to improve the overall power factor of the plant. The main thing is you have to understand from the V curves, for low field excitation, IF1 field current, this is called under excitation, and we have always a lagging power factor. Increasing the field current to IF2, this gives us what's called normal excitation. The stator current is minimum and the power factor is unity. So please understand that always when you have a problem and they're talking about normal excitation, they meaning that we are working at unity power factors. Normal excitation is unity power factor. Over excitation, when you drive the machine into a leading power factor. The last point we have, topic you will come across, is the synchronous condenser. The synchronous condenser is synchronous motor running at no load, which means literally as the synchronous motor is acting as a big capacitor or as a inductor. But normally we drive it at leading, overexcited at leading power factor to improve the overall power factor. So the synchronous motor, you can use it as a at no load. At no load. This is used in transmission lines. For example, you have a transmission line coming generators in Aqaba, coming to Amman, منطقة الصناعية بسحاب. There, the voltage, by the time you reach Amman, we'll have a voltage drop, and this synchronous mode condensers, there are there in the substation in Sahab, big synchronous condensers. What they do, they try to bring the terminal voltage of the transmission line back to its original value. For example, you start from Aqaba with 132 kilovolt voltage, line voltage. When you reach Amman, the voltage will be, it will lose about 10% or more of its value. So you use a synchronous condenser, which is acting as a like a capacitor to bring back this voltage to its original value. Well, I'll stop here. On the next video, we will do some problems. Bye.